I'm going to be talking to you about the Mallat Scattering Transform in high energy density plasmas. This is really a new look and a new paradigm on nonlinear physics and multi-scale physics in uh, general, but specifically I'll be talking to you about high energy density plasmas. The contributors to this work from Sandia National Laboratories, other than myself, are Thomas Moore or Matt Weiss, Daniel Ruiz, Chris Jennings, and Sophia Lucier from a theoretical perspective, and also then Pat Knapp, Eric Harding, Matt Gomez, Tom Muller, and David Yeager from an experimental perspective. And for David, I'll be specifically talking about some work that he did at the University of Michigan as a graduate student. And then also from Collège de France, there's quite a bit of input and suggestions and guidance given by Stéphane Mallat, the person who put together this new transformation. What I'll be talking to you about today is going to be a view on nonlinear physics. I'm going to contrast that versus linear physics, where linear physics is normally looking at linear instability and maximally unstable modes, where nonlinear stability is going to be examined through what is the steady state or time-independent solutions that lead to emergent behavior. This can go from a 3D normal cascade, where we see that there's a development of turbulence along with a Kolmogorov scaling, and then also in contrast to that would be a 2D inverse cascade, where things go to large-scale self-organization. Why do you go and get that self-organization? Because you go and have in 2D Navier-Stokes a conserved vorticity or amount of spinning, and there's no way that you can unspin the fluid without twisting it into 3 dimensions. But at that same time, you end up having a dissipation of energy to a minimum under the constraint of that conserved vorticity and a maximization of the entropy. The same thing happens in 3D MHD, because if you have in that case, you end up having a topological helicity invariant or a twistiness around a cylinder, and that you can't go and untwist it without moving off of those cylinders under a energy minimization underneath this constraint that also will have a maximization of the entropy. One major issue with nonlinear physics has been the lack of theoretical machinery in order to be able to analyze it. And that what I'll be presenting is a revolutionary new mathematics that allows one to make theoretical progress. First, I'll just describe what it is from a pedestrian viewpoint. How do you go and take this transformation and some of its properties, but then I'll go and connect it to the analysis of nonlinear physics, both from showing its relationship to an enhanced Wigner-Weil transformation and its relationship to an m-particle distribution function that is safe on a manifold. And a manifold, you can think of non-trivial topology like the surface of a torus in 2 dimensions. But also from a theoretical field theory viewpoint as the S matrix, or the sort of the multiple particle scattering cross-section as a function of the scale or the 1/over momentum. Then I'll go and talk about why is this important. It's important because we are seeing, I think fairly unequivocally, large-scale emergent behavior in maglev implosions. That's evidenced by mode merger, helical structure in the liner at a sort of modes below the linear mode with the maximal growth rate. that also we are seeing unexpected convergence to double helical structures with extreme convergence ratios in the maglev implosions. And then finally, since we now have a tool and we have a nonlinear system that is looking to have emergent behavior, let's go and use this tool on it. We've developed a regression from the helical parameters from the scattering transformation with uncertainty that's remarkably linear, and applied that to our stagnated images. We've developed advanced background subtraction that was needed in order to have an application of the Mallat Scattering Transformation as a quantitative metric of morphology between data and computer simulations. Okay, now let's just go and take a look at my the perspective on nonlinear dynamics in terms of a generalized master equation. In this case, you can go and see that the distribution function, one particle distribution function, is a function of p, where p can be 1 over a scale, a canonical momentum, an action, an energy, or the quantum numbers of a field theory or quantum system. And that's going to be the sources up to of that probability. Will be basically junk in from all the states p prime minus the junk out to all the states p prime. So we're looking at junk in from all the p prime states to junk out to all the p prime states. And that will end up being the probability that you actually end up being in p prime times the rate from p prime to pre. This rate is also the 2-particle distribution divided by the 1-particle distribution. Now what do people normally do? Well, within linear instability analysis, they expand the distribution function in terms of small perturbations. Then you go and get a dispersion relationship, some function that's now that is equal to 0. You can solve that for the p. You find that it has some wave-like oscillation with either a stability or an instability associated with it, and that all the theory really is around when is it unstable and what's the maximally unstable mode with the largest growth rate. That's traditionally what's been done, let's say, by Marshall Rosenbluth and many people up to that, through the history of plasma physics and high energy density physics. But now what happens when you're looking at a nonlinear system is you're really going in search of steady states, where if you now go into long time, they end up reaching a time-independent solution. Well, you just set the partial with respect to time to 0, and you now find all the stuff in minus stuff out ends up just being equal to your sources. If you're dealing with 3D, you end up having some source at sort of large scale. Then you end up getting an inertial or a steady state cascade in probability down to small scale where it's dissipated. And you can see here an example of an injection of a flow, a laminar flow at large scale that goes fully turbulent and chaotic. But in contrast, if you're dealing with 2D Navier-Stokes, I go in here at a medium scale. I have an inverse cascade into a probability container that fills up until it's full at a larger scale, and then you end up seeing a dissipation of the remaining probability at small scale. So you start with something that looks like this with a lot of little vortices as well as probably some larger ones, and then that organizes into a few large vortices. Well, what is it about this 2D Navier-Stokes that's similar to a 3D MHD. Well, with 3D Navier-Stokes, constrained to 2D conserves total vorticity or the spinniness of it, and so that you see that it has to relax in energy, maintaining the amount of circulation. In 3D MHD, that has both total magnetic and cross-helicity as topological invariants. It dissipates the energy and maximizes entropy, but it must maintain that helical twist. And so what we end up finding are these helical twisting double helices that even look a bit like DNA atoms with little axial hotspots at stagnation. Now let me turn to this new mathematics. We'll start by asking what is a wavelet transform, since this transformation is built off of it. A wavelet transform starts with a mother wavelet, and this is an example of a mother wavelet. And then this is then dilated or stretched to different sizes, and then it's convolved with a signal to give you band-limited signals at different scales or at different frequencies. Let's go and I'll show you how this is done in a little animation. You see the signal here in blue. You see the mother wavelet here at this position. And I'll go now and sort of sweep through 3 different scales to get 3 different wavelet transformations. Now we see the smallest scale sweeping through, creating the wavelet transformation at the smallest scale. We now go and see the wavelet transformation at the middle size scale, and now we see it at the largest scale being calculated. Well, there are some good things and bad things about Fourier transforms, which is the script, blue script F, and the wavelet transform, which is the magenta script W. That first of all, that the Fourier transform is not invariant to small deformations or stretch and squeezes, or what's called Lipschitz continuity, and you can see here why. That at very small scale, you end up seeing that they aren't the same, and that there's really no overlap. This, by the way, is the reason for the singularities in renormalization theory. It is invariant to sliding back and forth or translation, where it's just the opposite with the wavelet transformation. It ends up being invariant to the deformations, but it's not invariant to the translations. So what's the solution? Well, the solution is the problem, is built off of the problem that wavelet transformations are a function of time. That's why they're not translationally invariant. But it means you can take the wavelet transformation of a wavelet transformation. Here you see the signal with the dilated and translated mother wavelets. That goes and gives you a wavelet transformation. I can take the absolute value of that and then take the wavelet transformation of it. It'll equal 0 if I don't take the absolute value. Also note that I can't go and take the wavelet transformation at small scale of something where I've already limited it and eliminated that small scale. So this one I can only take at the largest scale, and the smallest scale I can only take at the next 2. I can't go and apply it twice at the same scale. And then you can iterate it again. What did Stefan realize that he should be doing? Well, for every mother wavelet, there's a father wavelet. In this case, it ends up being sort of a Gaussian window at the size of the largest deformation of the mother wavelet. And you can use this as a windowing function and apply it to the transformation. And now we end up taking this curve into a point, this curve into this point, and this curve into this point. Turn this on the side. We now have the first order scattering transformation, and we can do it with the other orders. But you now see that it is continuous to both deformation and translation. So we get the best of both worlds. Why ends up being, is it so important to go and have this Lipschitz continuity or the invariance under deformation? Well, it's because that nearly all of the equations that both in terms of kinetic systems as well as field theory and fluid equations, all in a way are a generalized diffeomorphism or a modification of a field or a distribution function underneath a vector field or more complicated tensorial fields. Here you go and see the most generalized form of it in terms of an n-particle distribution form, or it can also be a quantum field theory state that's now advected, that's what this little lead derivative is, by a vector field. And that this Lie derivative really is something that it turns out to be either commutator, a Poisson bracket, or things like v dot grad v, or acceleration dot grad position. We can now go and integrate this up and find it in terms of, say, the 1 or 2 or n-particle distribution function. We find that's also advected. But now we end up getting a collision operator on the right-hand side, which is the integral over the next higher order form. And we'll see this play out in the next page or view graph in terms of what that actually looks like. This turns out to be either a Boltzmann operator or that junk in minus junk out term that we see in the master equation. Okay. Now let's go to get to a generalized master equation, starting with the ideas of Bogoliubov. That F1, well, first of all, we pull back and we end up finding that we have two sort of normal coordinates. And we end up finding that we have an evolution of the one-particle distribution function, where this Lie derivative now is a Poisson bracket as advertised times something that is fairly close to a Boltzmann operator. We also can write a similar term for F2. Now F1 goes and has a very fast dynamical timescale which is associated with the wave oscillation or some type of atom-like periodicity. So that F1 on a dynamic timescale, F1 will now become a constant along that orbit. And then that sort of constant F1 will evolve on a much slower time scale associated with the collision rate. F2 will relax on this collision rate and will evolve at the correlation length. And that now underneath the separation of these rates, we can reduce these equations both to a Boltzmann form but also to a generalized master equation, where the evolution of the one-particle distribution function is nothing more than junk in the two-particle distribution function minus the junk out of the two-particle distribution function, as we've gone and seen before. But now, what are the pullbacks of these F1 and F2s on a manifold? Well, we're going to dust off some really old formalism dating back to 1927. But there was a real problem with this formalism where they tried to map operators down to a configuration space in terms of Q and P. And it was because of the fact they were using a Fourier kernel. But on a manifold, you end up having what's called a partition of unity, where you can only map patches. You can't go and map the whole manifold, in this case a torus, to R2. And so how do we have to go and modify this to make it manifold safe? Well, let's go and use as the partition of unity the father wavelets to go and give us these patch functions, and replace the Fourier kernel with the mother wavelet, which is a localized Fourier kernel. We now can go and take this transformation of the density operator, and lo and behold, we find it's F convolved with the wavelet squared. What we're really interested in is the f, which is kind of the square root of this operator, and the expectation value. To get the expectation value, you need to go and multiply it by the father wavelet, and you end up going and having the square root. Well, lo and behold, the one pullback of the one particle distribution function is the Mallat Scattering Transformation to first order, where the second order distribution function or correlation function, or the F2, ends up being just simply the second order Mallat scattering coefficient. We can also take a look at this in terms of field theory or quantum mechanics. We need to approach it from a Lagrangian perspective, where the important thing is the action as a function of the field. Then we go and we put in this generating function, and we find that the functional Taylor expansion of this generating function z ends up being nothing more than the, from a canonical perspective, ends up being nothing more than, again, the Mallat scattering coefficients. So that this ends up being the scattering cross-section of n particles into m minus n particles. Well, let's get a little bit more touchstone in terms of the first and second order scattering cross-section, define an effective action, expand it in terms of S and phi. And we find that what's important here is that the first order Mallat scattering transformation is nothing more than the classical action averaged over the quantum fluctuations as a function of scale, inverse scale. And the second order Mallat scattering coefficients end up being nothing more than the two particle scattering cross section, or 1 over the mass of the particle that ends up mediating the interaction. So this is the picture. We have a particle come in with a momentum p. It ends up scattering off of a particle of mass little m, which is the second order Mallat scattering coefficient, and the incoming particle has an action of phi naught, which is the first order Mallat scattering coefficient, and then it exits with a momentum p prime and an action that's now going to be phi naught of p prime. Okay, now if we end up going and we have something that's going to steady state, we end up finding that the Mallat scattering coefficients are now going to be constants in the motion, and that will allow us to construct canonical ensembles following the idea of James for all of these different type of systems. Okay, why is this so interesting? Well, at the University of Michigan, they ended up having they have a pulse power machine, and they also have the ability of taking quite a few different frames during one implosion. Here you go, and you'll see that the shape of the outer part of the liner is mapped across here in terms of axial position. And you can see that you end up having a merger of these small modes into much larger mode, where here is a merger event, and you can see that the average size gets larger and larger until it reaches some steady state. And the picture here is that we're really pumping here at sort of at this particular scale, and then it's carried out here at later times till it finally reaches an equilibrium here at fairly large scale. This is this particular organization persists during the implosion, throughout both the implosion and the bounce of the liner. And it's also interesting is that this is true for when we have a magnetic field and when we don't. But you can go and see here that there's really a continuous growing when we have m equals 0, don't have magnetic field, and we end up having a mode of m equals 0. As we increase the field, we see an organization through m equal 1 to m equal 2, but we also see a saturation in the amplitude. What's happening here? Well, you can go, and we're putting in some energy at this scale where you see this little red peak. We're getting an inverse cascade to down to this preferred location. But when Bz equals 0, there is no limit to the entropy. It can grow without bound. It has an infinitely large size probability container, so it keeps growing. But with finite Bz, the axial field, it limits the amount of probability of this container. It goes up to a finite level and then goes out. And you can also go and see it here where I've sort of flipped things so that you can compare what was seen in this case to this. This is also true with respect to both the Z-liner dynamics. It goes and persists through the bounce. But then also with respect to the self-emission images, you can here see a catalog of different self-emission images. We always see something with a helical twist. When we go and use an imager with higher resolution, we can see it separate into two different strands. We can see it look different, quote unquote, when we actually coat or change the helicity that's being injected into it. We end up seeing a good amount of yield, neutron yield from these stagnations. We have B confinement, and we also find that we have no emission without the preheat, that the energy stays well organized into these large-scale structures. Where if we don't have a magnetic field on it, we see we get no yield, no B confinement, and we get no bulk convergence. But if we go and have the magnetic field, that the size of the overall complex of strands is up to about 120 microns, but the size of each one of these individual strands is very close to the resolution of the spectrometer, and also there could be some temporal blurring of these strands since these are time integrated images. And the convergence ratio would therefore range from 38 to something greater than 200. I mean, this is really amazing. Okay, now let's go and start trying to analyze these stagnations with the Mallat Scattering Transformation. Here we go, and we formed up an ensemble of synthetic images based off of parameterization theta I and some other parameters that we called zetas, which were the stochastic ones. We chose a whole bunch of thetas randomly. We made synthetic images. We took the Mallat scattering coefficients of those images over 4 different patches, or sort of 4 different locations for the father wavelet. Here you see the first and the second order Mallat scattering coefficients. We then regress to be able to predict the thetas given the scattering coefficients. So that now if we're given an experimental diagnostic image, we can quantitatively form up what the thetas are and estimate what the thetas are with an uncertainty. Here I'm going to go and I'm going to be showing you the regression ensemble. These were all of the images on the left that we ended up forming after picking the thetas at random. What you see on the right is the predicted image where we took the scattering transformation of the image on the left, then used the regression to predict the thetas, and then reconstructed the image using the regressed thetas of the one on the left. Obviously, you can see they look very close to each other. It's a very good regression. Let's tear that apart a little bit more. We can take the covariance of the thetas with respect to the scattering coefficients, take the SVD of it to find the singular vectors, and in terms of theta, you see what these different combinations are. There are 12 of them because we had 12 different thetas. But what's important is you see the patterns you should be looking for in the scattering coefficients, be able to tell what these combinations of theta are. So now what you do is you take the scattering transformation of your target image, you dot product or project it into each one of these subspaces to be able to tell what these thetas are. Lo and behold, it's incredibly linear. Think about that. I mean, why isn't this bowed? Why isn't it a circle? Why isn't it a figure eight? Or even more complicated shapes? Something really is going on here that it can go, and with a simple linear regression, not a neural network, you can go and predict these things. And also you can see the correlation matrix. This is going back in the theta space, and you can see, for instance, between 9 and 10, there's a little bit of confusion, or they end up being correlated in terms of their estimates. This goes and shows, given an experimental image here, we're able to estimate the thetas with uncertainties. We now can go and form up an ensemble of what the predicted stagnation could look like, sampling from this distribution in thetas, and then randomly choosing what the zetas are. And that ensemble is what is shown here in the movie on the right. And then we ended up going in terms of a level 2 milestone this past year. We took different stagnation images, this in terms of a coded one, and on the right-hand side in terms of an uncoded one. We took the Mallat scattering coefficients. You can see they're different. But what's interesting is through the regression, you can see that for some of the parameters, there is a significant difference, like for these two. For other ones, they're very similar. Tommy Moore is going to be talking about this more in detail in his contributed talk on Friday. We also could go and did compare experimental images to simulations that should match them. We found, though, that there was a systematic striping of the experimental data. We ended up correcting for that by projecting out this background scattering transformation, and then we could go and compare the two. We found that the 4.5 aspect ratio simulation was very much like the data, the same for the aspect ratio 6, but we actually found that the simulation for the aspect ratio 9 did not match. Okay, so what ends up being our progress to date? I've showed you that we now have an understanding of the physical significance of the Mallat scattering transformation that allows, not only lets us know why it works so well, but how it should be used. And I'll be talking about two further uses of that. We've applied it to a regression to the helical parameters with uncertainty, which was part of the delivery of a level 2 milestone, and that's a remarkably linear regression. We also have used it for advanced background image subtraction, as well as quantitative metric of morphology, that is a steady state nonlinear structure or emergent behavior. In the future, we want to apply this to the radiographs as well as the stagnation images. We also want to derive the radiograph dynamics from the Mallat scattering coefficient of the radiographs. I think this ends up having also a potentially much larger use in terms of trying to use machine learning in order to integrate partial differential equations, but also this was to establish the connection between maglev implosion parameters, or how we are imploding the high energy density plasma to the Mallat scattering transformation of the stagnation image. Because we definitely want something on the right. We don't want that b equals 0 case. And as we scale up, are we going to go back to put that potentially that b equals 0 case? So in the end, we're going to use it to predict the scaling of maglev implosion morphology with uncertainty. That is, to establish credible scaling of the morphology in maglev stagnations. Thank you.